The broadcast is now starting. All attendees are in listen-only mode.
All right, looks like everybody's here. Thanks everybody who's joining us today for our latest webinar from SonTek about the key questions that you just might want to ask before you buy your next flow meter. So we're going to talk about Doppler meters today, the difference between different Doppler models and whether it matters.
Hi everyone, my name is Diego Davis. I'm the Western US Sales Manager and Technical Specialist for SonTek Products. Thanks for joining us today.
And I'm Janice Yasui. I'm the product manager for some of these flow meters at SonTek that we're going to be talking about. But before we launch into some of these technical details, here's our webinar agenda and kind of the flow of the information we're going to be giving you today. So first, we're going to talk about flow meters and how they work, just enough to be dangerous, because then we're going to talk about flow in open channels, what we know about that. And then what happens when you combine the two, the meters and flow regimes. So we're going to talk about, this is important because we need to know where the measurement's actually happening under the water. We need to know where biases can enter. We need to know how sediments can affect the measurement. After this technical piece, we're going to switch over into some examples from the field and some practical considerations. And lastly, we're going to talk about, well, once your meter's in the water, how do you know its accuracy? And then we're going to leave time for your questions. So there should be a question box on your screen. If they come up, please type those questions in and we'll get to as many as we can by the end of the webinar. And in all our SonTek webinars, if we don't have enough time to answer all the questions, we do answer all of those in a document. And if you've registered, you'll get the Q&A document after the webinar is over. So to set us up here, why is it important to understand how Dopplers work? Well, it's not important per se, but we need to understand a little bit because we're on our way to answering these important questions. So which is the best model to use? Why is there a price difference among different models? Can I trust the data? Is it working properly? How often do I need to check it? So you do need to have some basic understanding to answer some of these more fundamental questions. And, kind of how this webinar got started was, SonTek, we really pride ourselves in getting out in the field. And we do that because we have expertise to offer our customers. But at the same time, our customers are the ones using these instruments and dealing with different flow regimes around the world every day. So we learn a lot as well. And there's just a lot of practical knowledge that floats around, but you'll never really find that written down in an instrument manual per se. And so what we found is that there's really just kind of a gap in where this information lies. And what we're trying to do here is sort of put it all in one place and make it usable. And I know we have a lot of different backgrounds on the call today, and that's good. And it's true because Dopplers are used in a wide variety of environments to measure flow. So you can be a hydrologist measuring in open channels. You can be a water manager who's quantifying how much goes to a water district or to a farmer. It could be very operational. It could be for wastewater, or even we were talking to someone the other day who was using these flow meters for ecological studies, or even pollution loading, total maximum daily loads. You need to have flow information for that if you're under an EPA permit, for example. So lots of different reasons. Maybe some of these settings would resonate with you. All right, so before we get into the flow meter guts, I just wanted to get some terminology straight because there's a lot of different names that could be used when we talk about Dopplers. So you might hear the term ADFM, Acoustic Doppler Flow Meter, ADVM, Velocity Meter, AV Meter, Area Velocity Meter, or Ultrasonic Flow Meter. So they're all the same thing. They're all acoustic meters that go under the water. The one exception is, and this is why I don't like to use the word ultrasonic very much, is that ultrasonic can also be used for the kinds of meters that sit above the water. And I have a picture of one there that's sitting above a pipe flow. So ultrasonic meters can also be used just to measure the level, and they send an ultrasonic signal through the air. But that's just a level sensor. That's not a velocity sensor that goes in the water. So if you're using the word ultrasonic, just make sure you understand what kind of ultrasonic. We're talking about the instruments for purposes of this webinar that go underwater. And of course, there are many different ways to measure flow. I throw a few of them up there on the screen, and we're distinguishing the Doppler meters in this webinar today. All right, so when we're talking about Doppler meters, we're talking about two basic categories. There's what's called the Continuous Wave Doppler, and we abbreviate that CW sometimes. Show that here on the left. And it's usually a small sensor with a couple different transducers on it, and oftentimes there's a topside electronics box that goes with it. And I'll dissect this more in just another slide. And on the right-hand side, there's what we call Pulsed Doppler, and it's also called gated or profiling Doppler. And the model that we show here specifically, and the model that we use when we'll talk about Pulsed Doppler in this presentation, is the SonTek model, and that's called the Son Tek-IQ. So let's. I guess I should say also, if the Doppler system is not identified as pulsed, gated, or profiling, it's generally assumed to be a continuous wave Doppler. So let's start with the more basic kind of Doppler meter, the continuous wave meter. How does this work? Well, as you can see, it sits here on the bottom of the channel, and there's one transducer that emits an acoustic signal represented by this beam going into the water. And then the transducer next to it receives this signal. So there's a continuous wave, which is where the name comes from. There's a continuous signal being sent and received at all times. It's just one long continuous wave and one average that's being computed from all the data coming back along the water column. Now, the data that are coming back into the system are actually reflections from particles in the water. So we show that here. That's all the stuff floating around in the water. It's not from the water itself. So the particles that are in the water will matter in the ability to take a measurement and the quality of that measurement. When those signals come back, the instrument has sent out a signal at a certain frequency. When the signals come back, they're at a slightly different frequency. And how big that frequency shift is tells us how fast the water is moving. So let's move over to the more advanced kind of Doppler system, the Pulsed Doppler system. So you can judge just sort of by the naming that we use that the Pulsed Doppler is different in that it's not a continuous signal, it's a pulsed signal. So what happens is this instrument sends out a pulse of sound and then stops and listens along the same beam at discrete places in the water column. So the effect is that the instrument is measuring in layers from the bottom to the top of the water column. And we can divide up these layers up to 100. So you can get pretty high resolution with the pulse meters with the latest technology. And with both of these sensors, there's usually, or there's an option at least, for a depth measurement. In the case of the Son Tek-IQ, there's an acoustic measurement that bounces a signal off the water surface, and then there's also a pressure sensor. Most of the continuous wave systems have the option for a pressure sensor. And we won't dwell on it too much in this webinar, but you can see here in the case of the SonTek system, there's extra acoustic beams that go out to either side of the channel. So there are more acoustic beams than just the single beam of a continuous wave system. So here's just a slice real quick to show you how the Pulsed Doppler operates, because it's fundamentally different. There's this sort of programming that goes into the system's brain, if you will. And so the system thinks in terms of these layers, how big the layers need to be. And you can use this data in two different ways. You can use the full profile and look at all of these layers to do computations and analysis and flow. Or the instrument can just take all of this data and output one single average. And it could just be an average from the bottom to the top.
And
but
some of the, I wanted to mention
sure,
too, Janice,
Diego.
some folks on the call might be wondering, well, how does the IQ determine what the cell size is for each one of those cells? And there are two answers. And so, you know, the simplest form, IQ has a feature called Smart Pulse, which will automatically size the individual cells based on the water level that it's reading. And that's really just to optimize the velocity measurement. On the other side, for those researchers who are a little bit more intensive, you can actually program in fixed cell sizes. So there's a lot of versatility depending on what you're looking to do there. But the short answer is the IQ is smart enough to handle that that calculation for you.
Yeah, that's a good point. So our first sort of fundamental difference to notice about these two different Doppler systems is that even if you're working with an average, if all you care about at the end of the day is the average velocity for the average flow, that average number is calculated differently. So in the case of the continuous wave, again, it's just kind of an average of everything coming back in a continuous stream of data, and that's snapshotted and averaged. Whereas the Pulsed Doppler measures in layers, computes the average from that, all of that profile information, and then gives you one number. So that's the first fundamental difference. And so that's it in a nutshell for the basic operation of the two different Dopplers. So we're going to stop and segue to, you know, what do we know about flow fields? What do we know, Diego?
Thanks, Janice. We have learned a lot. And we're going to talk a little bit about measuring flow fields, how, you know, we kind of arrived at the design of the IQ. But here you see a picture of what seems like an ideal site. It's straight, it's clean, it's long, there are no obstructions anywhere in the channel. And, you know, SonTek has been a leader in studying and innovating around open channel and large cloud conditions. And so when we were developing new flow algorithms for the development of the IQ sensor, we actually went in with a flow tracker. It's a single point velocity sensor to map out and study what flow fields look like in a typical channel. On the bottom here, you actually see a theoretical representation of what you would expect to see in a flow field. But what we were able to learn in our studies is that this is rarely an actual, you know, an actual real condition. So these are actually, you know, what these sites end up looking like. And so on the top right, you can actually see one of the more uniform and predictable velocity distributions throughout our study. And what you'll notice right away is the velocity isn't in the center of the channel as you'd expect. It's actually skewed over to the right. I think this is something important when you're considering how your instrument is measuring the actual cross-sectional velocity, because if you just have you know, a sensor that has one plane of measurement just right down the middle and doesn't have the skew beams to measure what's going on along the edges, then it makes it real difficult for the instrument to actually capture the real conditions, and that could result in some bias in the data. You know, just to add a couple of points to that picture on the top, you know, the velocities, you know, decrease as you go towards the edges and towards the bottom, and that's expected. The figure on the bottom is actually a typical distribution. So for most of the sites that we were measuring, this is exactly what it looked like. And I think it's important to really point out that even at a, you know, seemingly perfect measurement site, Most of these sites were about 100 meters away from any sort of change in the canals. It's still important for the instrument to get detailed measurements of the velocity distribution to make sure that it's not calculating, some bias or just missing entirely what the actual flow conditions look like.
Yeah, I think kind of getting back to the intro I gave earlier, it's kind of no secret out there, among experts, open channel flow is sort of notoriously hard to measure. It's hard to pin down, and large pipes, which effectively operate like open channels. Everybody knows it's hard. It's a harder regime to measure in, but why? And that's kind of what we're going to proceed to sort out. What is actually going on that makes it more difficult than in a full pipe or a smaller pipe, for example?
So now I want to touch on, why the gated profile or why measuring in layers is useful. And the answer is that sometimes flow and sediment is steady and oftentimes it's not. So here's a couple examples of what flow gradients look like from a side view. And so this is a velocity profile from the bottom of the channel going up. In a typical velocity profile, as you see on the left in the figure that says normal flow, you have this condition where velocity moves pretty slow along the bottom because of friction, but also because sediments tend to kind of sit lower in the water column. And as you move up in the water column, velocities tend to increase, towards the maximum near the surface. And so that's an ideal flow condition, and that's typically what's programmed into theoretical flow calculation. And that can work if nothing is changing at your site and it's an ideal site. Other conditions that can exist are low gradient velocity profiles. That's a condition where the velocity near the bottom and the middle or the top is fairly uniform. There isn't a big difference there. And that can, skew your calculations if you're expecting a normal flow velocity profile. There's also conditions where you have a high gradient. So the velocity is low at the bottom, just like you expect, but there's a large difference as you move up through the water column. Again, that can result in some miscalculations. And then there's a condition where you can actually see reverse flows at your site. And so it's important to really be able to measure in layers because you want to be able to capture these conditions. Throughout one measurement cycle, your site and your instrument could experience all of these or some of these. And it's important to know when some of those shifts are happening and make sure that the instrument's able to account for all those changes. And so if there's anything you're going to take from this webinar, I think it's understanding that measuring the flow in layers gives you the information to measure changes properly.
Yeah, well put.
Another issue to consider is range bias. And what is range bias? Particles, just like Janice was talking about, is what we're measuring in the water. And particles can vary in size, they can vary in material types, and the distribution may affect the results. And so, like we talked about, particles can vary in size and composition and the reflectivity. Some particles that are larger or maybe of a different material might reflect a much higher signal than a particle that's much smaller or, of a less reflective material. And like we were talking about those velocity profiles, those different velocity profiles result in flow regimes that might suspend the particles differently within the water column. In general, heavier particles tend to move more slowly along the channel bed, and larger, heavier particles reflect more and stronger signals. So a good question to ask yourself when you're considering your site and which instrument to select here is, will the instrument be biased towards flow near the channel bed? In the case of continuous wave Dopplers, that's a real possibility. If you don't know where in the water column the reflections come from, there are a couple things you kind of have to accept here. The first is that the average of all the signals, you have to accept the average of all the signals being received. Like we discussed, a continuous wave system just sends out one beam, and along that beam path will average all the reflections and the Doppler shifts that it's seeing there. The next item here is that you may be getting more signal reflections near the bed because, like we discussed, heavier sediments that tend to reflect more are going to sit lower in the water columns. You might not be getting enough signals from higher in the water column to represent the mid and low surface velocities. And then finally, the measurement may be biased towards the flow near the channel bed. And so, just as a side note here, surface reflections might also bias the measurement in shallow water. And, if some of you have been out in the field, you'll notice during low water conditions or low water levels, wind can actually drive velocities along the surface and maybe even push water along the channel. So the instrument being able to know where the reflections are coming from are pretty important. Oftentimes, what continuous wave instruments have to do to account for some of these changes is that they're programmed with some sort of calibration or some sort of offset to be able to adjust the actual calculation. The issue with that, just like we saw and like we discussed before, is that these flow regimes can change. Sediments can suspend differently. So if anything changes within those conditions, the calibration may be off. So how do pulsed Dopplers handle this problem of range bias? I think it's important, again, like we discussed, to understand that the IQ and other pulsed Doppler instruments measure in layers. And there's a real strong reason for that. If you know where in the water column the reflections come from, louder signals near the bottom don't get counted more than weaker signals at the top. This is because the pulse signals are actually timed. So the instrument, pulsed Doppler instrument, will put a sound signal out, wait, and listen. And because that process is actually timed, we can do that throughout several layers in the water column and make sure that adequate weight is being given to the mid and surface velocities in the flow computation. Again, if you know, if you know where in the water column your velocity measurements are being taken, then you can resolve a lot of that bias and actually calculate properly. So now I'll hand it off to Janice.
Yeah, Diego explained the first condition that might occur, and I'll explain the next factor to consider, which is the beam angle and the potential range of the instrument that you're choosing. So continuous wave Dopplers often have more of a horizontal beam angle. So in other words, say 20 degrees off the horizontal, or some other number, which varies depending on the manufacturer and the model. But if the beam angle is more horizontal, which means skims closer to the bottom on its way to reaching the surface, it means that the signals have a longer distance to travel before reaching the surface. So if the signals have to travel a longer distance, there's more potential for attenuation of that signal before it gets all the way to the surface. And because we don't know where the measurements are being taken, we don't really know for sure how much attenuation is happening and whether we're getting data from the surface or not. So it's kind of an unknown. So what happens, so we don't know if there's going to be attenuation, but when there is, it might look something like this graphic with the contour lines, in that there's this unmeasured area at the top where we don't have signals coming back, and we might know it, we might not. Or when the depth changes, say it gets deeper, we might see this. When the depth goes shallower, maybe we won't. But that's a function of if the beam angle is lower and the signals attenuate. So how does this issue occur in pulsed Dopplers? Well, it doesn't, for a couple different reasons. One is that, at least in the case of the Son Tek-IQ, the beam angle is specified off the vertical, and it's 35 degrees off the vertical. So you can see in this picture, I know there's a few different beams here, but there's a more vertical orientation in the water column, which means there's a shorter path to the surface. So with a shorter distance to travel, signal attenuation is less likely to begin with. And in the event, you know, there's always something that can happen in the field, right? So in the event you're in deeper water or the signal attenuates, say the super clear water that you're dealing with, it can be verified whether you're getting signal from the top or not. Because remember, we measure in those layers. If signal strength is getting low near the top or becomes zero near the top, we at least know that. It can be verified and flagged, for example. So that's just a big difference in how the systems handle potential attenuation problems. So just to show side by side how this phenomenon could work. Again, you could have a beam angle that attenuates more, and you're getting data towards the bottom. It attenuates, so you're not getting signal near the top. In the case of the IQ, it almost always goes to the top. But what's nice about this picture too is that it highlights the instrument signals go out to the side as well, with the SonTek model in particular, because we have those extra beams. So the next particular scenario that we're going to talk about is what happens when you have low flows or zero velocities, or reversing flows, for example, where the flow is going one direction, it stops, and then it goes in the other direction. So the flow can get low or reach a 0 point. So continuous wave Dopplers, let's talk about them first. So in low and zero flows, remember those signals are coming back from reflections of particles. So when the flow is low, those reflections, that reflected frequency is going to be very small, and it might be 0. So remember, the continuous wave system is continually transmitting and receiving, and it can't detect a signal or a frequency that's different from its transmit frequency. So if you're continually sending and receiving and you're getting a 0 shift, you don't know whether that's the transmit signal or a true 0 reflection. And so this ambiguity imposes a minimum velocity specification. And continuous wave systems cannot measure below a certain point. So when you're looking at a continuous wave system, it is important to ask for and look for that specification if you think you're going to be in low flow conditions. So in contrast, the pulse Dopplers, because of the way they operate, are not subject to a low or 0 limit. This is because the pulse Dopplers pulse, and then they stop and listen. So there is a time when the transmit signal is not happening. So we know there's no transmit signal. Any shift that comes back 0 is a result of particles. And we know, therefore, when the particles and therefore the flow are at 0 or very low. So 0 or low flows can be measured very accurately with pulse Dopplers. So that's the last of our super technical parts. And if there's any questions, I hope people ask. Because we're moving now to some of the examples and the practical considerations. And who better to tell us about that than the guy in this picture who's actually installing the Son Tek-IQ, Diego.
I can't believe you all use that picture. That's actually me in a former life as a field technician. It's funny. So we're going to talk about some application examples, and we're going to start actually with an application by the city of Sacramento. And this is a very interesting application. It was actually a stormwater sump that, you know, and the final goal of actually using the IQs was to determine a chlorine dosage every time they had to run this sump. And so there are many challenges at this site. You know, just to kind of set the understanding here, most IQ installations, or most Doppler instruments in general, have a typical orientation of being installed at the bottom of the channel or a pipe looking up. And so in the condition that you actually have a full pipe, you can set the instrument at the top of the channel or at the top of a pipe looking down. And in this case, the users actually had to do both for good reasons. This stormwater sump actually caught all the stormwater, and a couple things happened. It was very susceptible to large debris, rocks, and boulders, stone-sized debris actually going into the sump. And then there were partial water, partially full conditions, as well as conditions where there was air entrainment up near the top. And so in order to be able to calculate or measure a flow and calculate a volume that was being pumped, what they ended up deciding to do was to install both an IQ up at the top and at the bottom to be able to account for any flow conditions that might be present. One nice thing about how they went about this is they wanted to at the bottom, they wanted to actually raise the instrument off the bottom to make sure that it wasn't damaged by any of the debris that could potentially go into the sump. So you can see this picture in the middle here on the bottom. They actually created almost like a shark fin to get the instrument up off the floor, but also keep this hydrodynamic design and reduce any sort of turbulence around the instrument. You can see the picture at the top. They actually were able to create another mount that protected the IQ as well, but also just kind of kept with that hydrodynamic design. In the middle are actual screen grabs from the channel configuration, and this is something we'll dive into a little bit more with respect to the software. And these are really nice visuals for just understanding where the instrument is located, how it's oriented, what the pipe diameter is, and just confirming that the instrument is programmed properly. At the end of the day, what they ended up doing was installing these instruments, using 4 to 20 milliamp outputs from the instruments to tie back into SCADA, and they were able to, view flow conditions in real time to make sure that they were dosing this stormwater with chlorine properly, which was part of their requirement at that site.
And if I were to understand correctly, was the accuracy requirement around doing that chlorine dosage that really sort of made the IQ the choice here?
Yes, exactly. Just the amount of turbulence you get when you start running these pump conditions, in addition to all the different flow regimes you can see at different water levels, it was important for them to really understand what the true flow number was.
Right.
And in their test with the IQ, they trusted it enough to use it that way.
Yeah, that's a good point. When you have pumps or other artificial inputs into your flow system, that's a big signal that you could be having more complex or changing flow regimes. Mm-hmm.
Another application was actually conducted by SWIM, who is an integrator out of California, and they were actually doing some work for the Metropolitan Water District. And so before they actually decided on what instrument to use, they did a side-by-side comparison of a Flume, a gray line AVM, and also a Son Tek-IQ. And after going through all this trouble, the most meaningful feedback we got from them is right here in quotation. The result is that we ordered 15 IQs and haven't spec'd any more of the other devices. So they actually, did a trial, tested all these different conditions, and ultimately decided on the IQ, not just because of the immediate quality of the data, but I think for the long-term condition or the long-term considerations for installing these instruments, maintaining them, and ensuring that they were getting real good value out of the instruments that they selected and minimizing any sort of errors they might run into in the future. To kind of elaborate a little bit more on the application, all the sites were, fairly small trapezoidal channels, 2 feet bottom width with a 1-to-1 slope and a maximum of 3 feet of depth. They would typically run anywhere from 25 to 35 CFS. And they started with 15 IQ installations, and in the future are considering up to 200 sites. One thing that's important before we move on is to do periodic checks on these instruments. As great as the Pulsed Doppler instruments can be in tough conditions as well as ideal conditions, it's important to do some sort of periodic check. In this picture here in the middle, we can actually see one of our sales reps, Michael Sundman, who handles some of the Southwest states. He's there with a flow tracker too, which is again a point velocity system that's used to measure the entire channel and validate a flow rate very accurately. And so this is just one way that you can do a periodic check on these instruments to validate their accuracy and performance. Whenever you're considering any sort of instrument for the field, it's important to make considerations for installation and maintenance. One thing that you'll find with a lot of continuous wave systems is that they have their actual cable built in to the transducer. And as you can see, the Pulsed Doppler IQ system does not. And so why is that important? I think it's really important primarily for installations. During an installation, especially if you're planning to run your cable through conduit, if you have your sensor, if you have your cable built into your sensor, it really makes it difficult or it really limits your options for routing that cable. Obviously, you'll want to route the cable from the actual installation site up through the conduit and to the top side. But depending on what your site looks like and how you actually have to approach your installation, you might want to go the other way. And so there are some limiting factors there. If, let's say you're going from the top down to where the site is, and you're using a continuous wave instrument, you'll actually have to try to get that sensor head through your conduit, which could need adding some sort of junction box, upsizing the size of your conduit, and making your installation a little bit more difficult. Another thing to consider is what happens if the actual system gets damaged. I think a really convenient thing about the Son Tek-IQ system is that you have this detachable cable, and if anything goes wrong, you can assess, is it an issue with the cable or is it an issue with the instrument, and switch those items out to reduce your downtime. In a continuous wave system, you would actually have to pull everything. You'd have to pull the sensor, you'd have to pull the cable, and then you'd also have to understand how badly it was damaged, if you have to send it back. And there's additional downtime, I think, in going through that whole process. The last example we're going to touch on here is a Son Tek-IQ example with Natomas Water out of Sacramento. They manage a big system where they have several different types of sites, open channels, pipes, and so they use a variety and a mix of different IQs as well as IQ pipes to manage their system. And at this particular site, they're actually able to consolidate 2 IQ pipes and 2 IQ pluses into one SCADA cabinet. And I think, it was really convenient that the design of the IQ flow display as well as the cable was really slim and compact so that they could get everything into one entire SCADA cabinet. One thing you'll actually see with a lot of the continuous wave systems is this kind of large power control and display, and that's required to run the instrument. And so if these folks were to actually go with that kind of solution, they would have to set up 4 of these enclosures within this big enclosure. And those kind of bulky displays really take up a lot of real estate, which would mean that they require a larger enclosure, or they might even have to do 2 separate enclosures. So just something to consider, the slim design and the kind of compactness of the IQ and all its accessories really help out a lot for creating these final products for a district.
Yeah, that reminded me, Diego. I don't know if we stated explicitly before, but if you can assume from the pictures, perhaps, but the IQ systems don't have a topside box. All of the instrument processing and the electronics go inside. Yeah. So what you're seeing here is just displays. So if you want a digital display to walk up to, you can, but those are optional, and you don't need anything topside except your power source with this model here.
And it's important, I think, to kind of understand that too. In its simplest form, you can hook this up to a battery inside of a small weatherproof box and have the IQ running just off that battery, sitting on the side of the road. So it can be very simple, or it could be as sophisticated as what you see here. So on the topic of installation and maintenance for instruments, I wanted to highlight this excerpt that I saw in the manual for a continuous wave instrument to really make a contrast between the quality and the thought that went into the engineering of the Pulsed Doppler IQ system. You know, when SonTek designed this instrument, they really tried to understand the market base and build in meaningful features to make sure that the instrument was adaptable and would fit into you know, any challenges in most applications. Here's an example of you know, what should be something fairly straightforward. In this you know, piece, in this little excerpt that I took from a manual, there's some pictures here that actually walk you through the process of installing a module that will enable a Modbus output or an SDI12 output. And so, you know, as we read through the instructions here, you know, it starts by telling you to open the enclosure and ground yourself on the circuit board, then remove, you know, the 3 screws that are inside the enclosure, being careful not to drop the screws inside the enclosure for the risk of damaging the electronics, and then grounding yourself again, and then taking your card and grounding yourself the entire time that you're putting this card in there. I think if you were to try to do this out in the field, there's a lot that could go wrong. Additionally, you know, even if you were in a controlled work benchtop setting, there's a lot that can go wrong. And I think when you contrast the 2 instruments, one that already comes with these features built in a nice, compact, clean design, and you look at something like this, there's an obvious difference in the quality of engineering, which, you know, I think speaks to or ends up resulting in kind of the ease of use for the end user.
Yeah, that's a good point, Diego. There's the sensor that goes under the water part. There's that technology, and then there's, you know, the electronics and integration technology.
Additionally, user interface is important for these instruments, and making it easy to program and download data is an important part of considering any sort of instrument. Here's an actual menu tree, and what this is there are continuous wave systems out there that do not have any sort of software. So the way that you configure them is that you use the few buttons that are on the front display to go through the different menu screens. In the top side box, right? This is the top side box. This is the little display in the top side box. Yeah. Correct. And by navigating the different screens, you're able to configure your instrument, you're able to download data, put your calibration coefficient. This can be fairly tedious. I've played with menus like this, and you can definitely get lost in where you are in the menu. And I think it's important these days to have some sort of software that you know, provides you a lot of the visual cues and easy to understand. This is an example of the Son Tek-IQ software. As you can see, it's very clean, it's modern, and it has a very intuitive configuration menu. On the left, you can see what an actual configuration menu looks like, and it's very easy to understand. You go from the top to the bottom, starting with your most simple parameters such as time, date, your file name, site name, and then moving on to your channel shape and entering in a geometry, and then so on, putting in unit outputs and what your channel and what your data outputs are going to look like, maybe Modbus or RS-232. On the right is a screen grab of actually programming in the geometry. In this case, you know, for the channel type, we chose a trapezoidal open canal. So on the right, we actually have this graphical representation that shows all the measurements that we put in, what the base distance is, what the height of the canal is, what the top width is, and where the instrument is located. And so I think it's really important to have this meaningful visual to really check and validate that, yes, my instrument is set up properly, and I can start measuring and expect that I'm going to get the data that that I'm looking for.
I think the other good point to make here is that, you know, experts will know that, you know, instruments these days are pretty darn accurate, and a huge source of error actually comes in with the user, him or herself, to know whether you've installed it accurately. Where you put it is where you actually put it in the program when you calculate the discharge. Because remember, these instruments output a velocity. That's the real measurement, and flow is, or discharge is, a calculated parameter, or total volume is a calculated parameter. So the instruments can measure velocity, pretty darn accurate, but that calculation, that flow number, depends on the user. So if this channel geometry isn't precisely programmed or known, then you're introducing error in essence. So that's another source, that's a slop factor that I think people encounter, that once you're aware of it, you can do something about it.
Here's an example of a data display for a configuration file for a continuous wave system. So on the left is an actual view of a data file within the software. As you can see, there's some header information, some status messages, and also some timestamp data, which is data separated by commas. And it's a fairly basic, way to see the data and try to read it and understand it. On the right side is an actual configuration file, and so here you're able to see how the instrument was set up and which options were selected. I think if you kind of contrast back to what the configuration looks like for the IQ, you'll see, there's definitely a big difference there in viewing and understanding how this instrument was set up. On the next screen is an example of what a data display looks like for an IQ. When you open up a data file, by default, you'll get these two parameters that you see graphed here for flow and depth. But you can program up to 4 different graphs. You can overlay different parameters. And the third graph here, which we included, is a graph of the velocity beam data. So this is data from each individual velocity beam. On the right, we actually have a profile of our signal to noise ratio, or signal strength, for each individual beam. And this is something the instrument does in the background to understand what the quality of each individual beam is and ensure that the instrument is operating properly. And finally, on the bottom, we have some tabular data for all the different samples that we can scroll through. There are several different fields here, which are user customizable. By default, you'll get all of them, but if you don't want to see all of them, you can reduce those number of parameters down to ones that are, of particular importance to you. And the last thing I want to touch on when it comes to, the software and some of the features with the IQ is the Smart QC feature. The SonTek is capable of generating and logging smart error codes based on an extensive catalog of real-time conditions. Some of these conditions can include things like low system power, perhaps the system's moved, or the beams have become buried. And what's nice about this feature is it can report a single error, or it can report a combination of errors that it's experiencing in real time. If for some reason those conditions resolve themselves while the instrument is measuring, that error will be cleared. What's important, I think, with this whole idea, though, of Smart QC, is that it gives users an understanding of when an error occurred and it logs it. It can also be used as some sort of output for a SCADA or monitoring system to understand that, hey, I have my system's moved, or I see that my beams have become buried, or anything that might be going on. It really gives a user valuable and meaningful data for understanding what's going on out in the field. And if you're reviewing data and seeing that there are some ambiguities, having this feature to log some of those errors is really important in justifying what happened there, and perhaps even avoiding those issues in the future. And with that, I'll turn it over to Janice.
Yeah, great. Those are some great practical considerations. Thanks, Diego. So the last, question we haven't answered yet is, how do we know it's accurate? Any flow meter that you put in the water, of course you want to know, right? So the quick answer, we could do a whole different webinar on this, but the quick answer here is instantaneous discharge measurements. And if you have no other reference, or the whole point is that maybe you're questioning your reference, or you have two references that are differing, this is the method you would use. I show a couple different options for the acoustic instruments that are out there. You can also use the old-fashioned propeller kind of meters as well. So the top, for example, is an instrument called the SonTek Flow Tracker, and it's an acoustic probe that you just put in the water. Both of these require a person to operate them. In the top case, the person gets in the water and moves from the right to the left bank and measures at points along with the depth. And then these measurements are gathered, thrown into a calculation. I'll show you that in a second. And an accuracy number, and the uncertainty around that accuracy number is also output. If you have deeper water, you can use something like an ADCP that's shown below here, Acoustic Doppler Current Profiler. These instruments go deeper. You don't have to get in the water. And then there's still software that you interface with to take those measurements. They can be used in large rivers, or as you can see here in this hydroelectric plant, in narrow situations as well. Same method for both instruments, but of course when you're using the ADCP that samples 70 times a second, you're getting really fast, high-profile data. But this is the basic measurement concept that's used. This is an international standard. There are variations depending on what country you're in. And in the case of all SonTek instruments, report is generated, and there's two different methods that we use here, the ISO method, or the IVE method. And generally a criterion that's widely used by experts is if it's a 5% or less, it's a good measurement. But of course, if you can do better than that, you want to do better than that. But this is the ultimate output of a continuous, an instantaneous measurement instrument. So what happens? You can put these two together, right? You can put your fixed measurement, in other words, your continuous discharge instrument, like a Pulsed Doppler or a Continuous Wave Doppler, or a propeller meter, or even a side-looking Doppler. There's other configurations of Dopplers. So you can see that one on the left there. It's a side looker. So you can have your fixed mounted instrument, but if you want to check it, you would put one of these ADCP or weighting measurements in the water, do a really accurate snapshot, and then check it against your fixed mounted instrument. And if you really want to make it accurate, you'd move beyond just simply checking the measurement every now and then to actually building a curve of your fixed mounted instrument with the check measurements. You'd build a curve and get an equation, get some coefficients, plug that back into the fixed mounted instrument, and make it even more accurate. And so what I just described is how I would call a site calibration. Calibration is one of those words that you do also have to take some care with when you use, because Doppler instruments themselves don't need to be calibrated unless they're damaged. And you can check the calibrations, but it's a matter of physics, the way the beams are pointed. When we talk about calibration, usually what we're talking about is site calibration. So again, site conditions can change. And especially in the case of the continuous wave instrument that doesn't know how the flow regime is changing, calibrations are attempted. So if you apply calibration to any instrument, it will improve the accuracy. Now, maybe you can infer that it takes people to operate these instruments, do the check measurements. So that would be something to factor in your overall operation schedule, your instrument needs, and your budget, quite frankly, if you do need to go out there and do a lot of calibrations to check the instrument accuracy, or continually perfect the calibration if it's not quite right the first time. And that takes us to the end of the webinar. Thanks everybody for sticking it out with us. If I were to summarize it again, it would be a lot of words like you see here on the screen, but this is actually from a tech note that we also put together on these subjects. If I were to summarize it real quick, as Diego mentioned earlier, pulse Dopplers measure in layers, and water flows in layers. So that would be our main takeaway. If there's bias potential, you want to consider how the instrument would work in your environment. based on what's going on in the sediment or attenuation possibilities. You want to think about the depth requirements, whether you have low velocities present, what your overall accuracy needs are for the application, like that chlorine dosage example, for example, and then what your interface needs are. What do you need topside, and what would work best? And then here's my little, emoji communication of the thesis here. So at the end of the day, any flow meter could possibly be the right one, but think about what factors can possibly affect the measurement. Due to the instrument, how they operate, what could happen. Due to the environment, whether your environment's changing or what the flow regime could be, and then how the two fit together. And then how the two fit together ultimately gets you to what you really want to know, which is, can I use this data to make the decisions that I need, or be confident in what I'm putting out there to the public? And with that, we have a few minutes left for questions. So why don't we move over to the questions that we see here. So yeah, this is a common question on everybody's mind. So what is the cost difference between continuous wave and pulse systems? So Diego, do you want to take this one?
Yeah, I'll take that one. So it's kind of hard to give an actual dollar value because there's probably an international audience here, and prices vary depending on where you're purchasing this instrument and what currency. But in general, you can make the assumption that continuous wave systems are maybe 2 to 3 times cheaper than a Pulsed Doppler system like an IQ, or you'll find a couple other ones from different manufacturers as well. But I think it's important to really understand these two types of technologies and what the value of each one of it is. In the case of Metropolitan Water District, right, they're looking at the long-term maintenance costs of this instrument, and even further, what the repercussions are of miscalculating data. When you kind of put a dollar value to that, it's important to make sure that you have an instrument that's going to reduce the amount of time that you're spending checking the instrument. If there's any question about the data, you'll have to go out there, make sure your calibration is correct, maybe send a specialist out there to go verify the data. And that's a whole cost in itself. There's also the issue of maintenance, repairs. And when you look at an IQ or a product like an IQ or a Pulsed Doppler, the quality of engineering that goes in there just really makes it so that, for the life of that instrument, you're really getting your money's worth. And overall, you're going to be paying a lot less, than you would by operating a continuous wave system. So, if I was to reiterate here, you can definitely get cheaper continuous wave systems when you look at, the longevity of that instrument and all the costs involved with making sure you're getting good data. It's important to understand the value of an IQ.
Let's see. What do you mean by blanking distance? So this gets back to kind of the principle of operation of a Pulsed Doppler instrument. So it is good to point out, it is fair to point out that if we're doing a compare and contrast here, a continuous wave system doesn't have a blanking distance. It's doing a continuous stream of sending the signal and receiving the signal. So there's really no waiting period in a continuous wave. So it is true that continuous wave systems can operate in shallow water from that perspective, and that there's not as much of a blanking distance. Now, you might have to worry about surface reflections. That's a different issue. But in terms of blanking distance, that's a Pulsed Doppler thing. And if you remember, it's because the Pulsed Doppler system sends a short signal, a pulse, and then there's a fraction of a second where it stops to listen. And in that fraction of a second, there's a blank. There's a blank where there's no measurement happening. And these days in a Pulsed Doppler system, it's a couple centimeters. So it's not very big. It's just a little bit close to the surface of the instrument. but that is a zone where no measurement is happening. Next question, is one system better than the other when dealing with debris?
Yeah, I'll take that one. I think in general, both of the systems are going to perform, you know, the same with debris. So they're both, especially systems that are bottom mounted, looking up. They're both susceptible to burial. They're both susceptible to large debris, vegetation, things like that. And so I think they're both gonna, in terms of can an instrument get fouled? Can you have some debris that's gonna affect the data? Sure. But I think there's also some important features, you know, with the Pulsed Doppler IQ, specifically your Smart QC feature. That instrument is going to tell you what sort of condition you're running into. If for some reason one of the beams is blocked, multiple beams are blocked, you have debris or damage, low power, whatever you might be experiencing, the instrument will actually log that error and either report it through some sort of real-time system or log it internally for review later on. And so I think that's a really important part of the Pulsed Doppler IQ system when you look at some continuous waves. I know there are definitely other error codes for continuous wave systems, but I think the level of sophistication of reporting those errors and identifying them in real time is on a much different scale than what you'll find with the Son Tek-IQ products.
And what about the power requirements?
Yeah, and so this is something I have a lot of experience with. The IQ is a fairly low power instrument. You know, it requires a 12-volt DC power source, but that actually lends itself to all sorts of applications. So when you get the whole package of equipment, you'll actually get a wall inverter so that you can convert 120 over to a 12-volt signal, and that's the easiest way to power it. Just plug it in to the wall, plug the connector into your power communication module, which is a small little brick, and there you go, your instrument's live and ready to go. But the low power draw and the low power requirement for the IQ also makes it a really easy instrument for remote field collection, remote data collection, and you can hook it up to a small battery and a small solar panel, and you know, run it continuously as long as the battery is good for remote field data collection. So yeah, there's a lot of versatility in the power requirements. It's a very low power requirement, and it kind of comes with all these different options for setting it up.
Mm-hmm. Let's see. Pulse Dopplers are unnecessarily complicated. You know, I would say Pulse Dopplers are more sophisticated. You can just tell by looking at those graphics that we showed that dividing the water column up into layers and then measuring in each layer is more sophisticated, and it's certainly a lot more data that's going into the calculation. And there's fewer assumptions being made because you have more data. So it is, I will acknowledge, there is more data there. But as Diego pointed out, the instrument also has the brains inside to handle all of that. So it's really, you know, with the technology these days, you don't really have to set it up any more or less than a continuous wave system in terms of what goes on underwater. Yeah, and if you want to have that kind of control, you can get involved in that, but you certainly don't have to. You can really just install it and get it running and get a very accurate flow number. Let's see, maybe we should make this our last one since we're already over by 5 minutes. So thanks everyone for your questions. If we didn't answer your question, we'll get to it. So our last question is, we'll get to it in the Q&A document rather. Does SonTek do installation and rentals? Yes, yes. Well, we have a list of people who can help you with that. Is the short answer. So Diego and I don't personally do that in our offices, but we can definitely help you with that if if you want to try it out or have a short-term project or something. All right. Well, thanks everybody. I'm gonna sign off here, and thanks for joining us. And you'll be getting a follow-up email from us with some more references. We actually have a calculator tool that just went live on the website. So if you actually want to calculate in monetary value what the error percentage of your flow measurement is, if that's something you're doing as a water manager, give that a try. So we'll give you some links to that. We'll also throw in a special offer for you. So be on the lookout in your email. Thanks, everyone.
Thank you, everyone. Have a good day.
Bye-bye.